All right, so I'm just going to show off the Empower simulation environment real fast. So essentially Empower just allows you to simulate smartphones traveling around an environment and putting in data readings, etc., etc. So you can choose KML to represent the geographic environment you're interested in. And then in this particular example, I'm going to be attempting to measure the cell phone signal in various regions of the environment. So I've just got some basic network coverage graphs that are defined as images. So I'm going to start out with one coverage graph, and it'll take quite a while to load this up as the simulation loads the graph in memory and sets up all the smartphones in second and stuff. So hopefully in about 10 seconds here, we should see it pop up on the screen. All right, so here we go. Okay, so what we're looking at here is a graph that's being generated. And if I press R, you will see the real network shown on the screen. So this is what really the smartphones are trying to see. And now we're seeing a new real network being loaded in. So and in the middle of the execution, the network has changed. And if I show you the perceived network, you'll see that once smartphone readings start coming back in, this current perceived network will start updating to that new real network. So essentially what's going on here, you can have basically a static network, and you can measure the number of smartphones it takes and how long it takes for you to achieve coverage or accuracy of that static network. Or you can have an arbitrarily dynamic network, loading in new networks as you go that are slightly different from each other. And you can actually measure, what is the effect on overall system metrics? How dynamic of a network can we measure with the number of smartphones we have, with the properties that those smartphones currently are existing, et cetera, et cetera. So I'm going to go ahead and escape out of this and just show some interesting graphs. So let's see, we'll start off with this one. Yep. All right, so essentially this is for a static network, and on the left here, on the left side is the accuracy, and down in the bottom is the simulation time in hours. We're around 1,400 hours, so about right at 3/4 mark there. That simulates around 2 months of time. So what we're seeing, obviously, is in a totally static environment where nothing is changing, as the time goes on, hopefully the accuracy of the perceived network when compared to the real network is increasing, which is exactly what we're seeing here. The major divisions of lines are the number of smartphones. So down at the bottom, these two are 200 smartphones are in the environment. In the middle is 500 smartphones, and up at the top here is 1,000 smartphones. And then one of the other things I'm actually comparing here is two different data collection policies. So we have one data collection policy that says always collect data. It doesn't matter, just always collect data, which, as you can probably understand, leads to a lot of wasted input readings where somebody is collecting data and sending it to the server, and the server is getting absolutely nothing out of that data. It was totally useless. So we're comparing the accuracy under a constant data collection policy, which, as you can imagine, is the higher line. So it's slightly better if you're always collecting data. And the lines below those are the context-aware data collection policy, where people that move more frequently are asked to collect data more frequently. So as you can see, the accuracy is slightly lower. Interestingly, though, we thought that this was going to be a substantially lower decrease in accuracy. In fact, the biggest measured effect was less than 0.5% of accuracy, so 0.05%. And we were able to cross-compare this graph with the number of wasted readings. And it's actually very interesting. The context-aware policy wastes far, far fewer readings, but you only sacrifice a tiny, tiny bit in accuracy over time. So it's probably worth it for most situations. So that's one graph. So that's a static environment. So now let me show you accuracy for a dynamic environment over time. And so these major dips in the graph, these major drops in accuracy, these are actually when I've loaded in a new real network. And so you can see that I'm doing it pretty infrequently here. I'm only loading in a new network every 200 simulation hours or so, which, 200 hours in real time. So, I guess that's, all right, there you go, about a week in real time. So about once a week, I completely change the graph. Nothing is the same. And so you can see the accuracy dropping and then recovering from those things, which is fairly interesting. And then this is just another example graph. So what this one is showing us is for a totally static environment, so nothing is changing, and for the constant data collection, aka always collect data from every smartphone no matter what. So the blue line right here is actually showing us the accuracy over time, and there's a tiny rounding error, so it's not it's a little bit over 1 because there's a small rounding error. There's actually, I'm not too concerned about that because there's, around 10 million calculations being performed in order to reach this this one number. So not terribly concerned. But so the red line, though, is the interesting one. And what this red line is showing us is of all of the readings that came in, what percentage of those readings provided absolutely nothing in terms of an improvement to the overall accuracy measurement. And you would see exactly what you would expect to see here, which is as the accuracy goes up, the number of readings that don't give us any sort of benefit in the accuracy department also goes up, which is interesting. And then I've got a different kind of graph where I've created the, quote, usefulness of each input reading. The usefulness is actually expressed as a percentage of the accuracy. So these numbers on the axis, on the vertical axis here, are very, very small because there's only a tiny percentage in accuracy increase for each individual reading. But again, you see kind of what you would expect as the as the accuracy is going up, the usefulness kind of goes down inverse exponentially. Interestingly, we can load in multiple real networks, and you'll see this usefulness spike back up for those real networks. So anyways, it's just a basic example of some of the capabilities of the Empower environment. So hopefully some of you guys are enticed to work on this.